Perfect. Can you all see my screen? Yeah, okay, cool. Sounds good. Hi all, my name is Mayank Agrawal. I'm a PhD student at Princeton University, and I'm going to be talking about a recent paper of ours called Scaling Up Psychology via Scientific Regret Minimization. And this is joint work with Josh Peterson and Tom Griffiths. So one of the most kind of recent high-profile big data experiments was this moral machine experiment. And so this was published kind of at the end of 2018 in Nature. And for those of y'all who are not familiar with it, it's kind of based on the trolley car problem. And so in the trolley car problem, there's this runaway trolley headed towards 5 railway workers. And the question is, do you let the trolley continue and kill those 5 railway workers, or do you pull a lever and let it switch and kill a kind of 1 railway worker on a sidetrack? And what the moral machine researchers did is they kind of adapted this to autonomous cars, kind of thinking that autonomous cars might have to face kind of similar types of dilemmas in the future, and it would be interesting to crowdsource what kind of people's beliefs on what a car should do. And so I'm going to focus on a paradigm where there's an empty autonomous car headed towards 2 sets of pedestrians, so one in front of it and one on the side. And so here, there's an empty car headed towards a girl, an old woman, and a dog who are crossing illegally. And on the other side is a child, a woman, and a dog who are crossing legally. And the participant is just simply asked, should the car stay or swerve? And so there's 20 different characters, and with the crossing signal configuration on the side of the car, you can see that this is going to be a really rich problem space. And so the moral machine researchers collected close to 40 million decisions and for people over 200 countries. And so this was kind of a very interesting data set that we kind of just wanted to analyze and see, what value does this data set bring that traditional, say, trolley car experiments could not. And so the first thing we wanted to do is we just wanted to see how well can we predict people's behavior from kind of psychological theory. And so what we did is we just created these rational choice models. So you have pedestrians on the left side, you have pedestrians on the right side. We're going to say, okay, what is the value of a side? And that's just me, like the number of women on the side times some weight, the number of men on the side times the weight, the number of girls, the number of boys. Each of them are going to have its own weight. And then you calculate that for the left side and the right side, and then you just apply kind of the softmax over it to identify what the probability is of killing or saving one side. And so this is really just a logistic regression model. And so we kind of created 3 of these logistic regression kind of choice models corresponding to different psychological theories of moral cognition. So the first one was just a utilitarian. And so here, the value of the side is going to be completely comprised of the values of the characters and the values that you would lose from essentially killing these characters. So this is essentially here are the 20 characters that you had, and we kind of inferred what the best weights were for these 20 characters. And so this is just a logistic regression model with 20 features. Then we talked about a deontological model wherein there's going to be 2 kind of fundamental moral principles at play. So one is that if you're crossing illegally, you're going to be penalized. And the other is if you need to swerve, then you're going to be penalized as well. And so we just kind of inferred what the weights would be for this logistic regression model with 2 features. And then lastly, people aren't completely utilitarian or deontological. There's some hybrid. So we just kind of put all these 22 features into a model and just see how well we could predict them. Great. On the other hand, we also wanted to see, how we wanted to really exploit the fact that, we just have millions and millions of decisions. We can just use, tools off the shelf from machine learning. And so what we did is we also just trained a neural network to identify, how much of the data is predictable in itself, right? We wanted to see, the logistic regression was going to do well, but the neural network would probably do better. And we wanted to see, what is the upper bound on the explainable variance in the data set. And so what I'm plotting here is the AIC, the AUC, and the accuracy. And on the x-axis is going to be data set sizes. So we got subsets of data for different sizes, and we just kind of trained, on 80% and then tested on a held out 20%. And we did this for the neural network as well as for the three logistic regression models. And so I'm going to focus our attention on the green hybrid model and the red neural network. So you see the hybrid model does really well at the beginning, but one thing that's really interesting is it's kind of flat as a function of data set size, and it doesn't kind of really improve well with data set. And, the left sides of the graphs are, where the standard psychological studies are usually the size of standard psychological studies. And we see that these logistic regression models are really good. On the other hand, we see the neural network doesn't perform as well at these small data set sizes, but once it gets enough data, say on the order of 100,000 dilemmas, then it starts to perform very well. And it starts to surpass kind of the logistic regression model. And so now I'm going to say, there's kind of this tension. So, we wanted to predict people's behavior, and in terms of that, the neural network performs better than the kind of hybrid choice model. But, the hybrid choice model is really interpretable. It's a logistic regression model with 22 features, and the neural network is just this, black box, like 2,000 parameter kind of model that we don't really know what it's kind of getting at. And so, ideally, I think as psychologists, if we were just like pure machine learning researchers, we might just like, stop here and be like, okay, neural networks are great. But I think us as psychologists also want to get some explanatory insights into, what is the neural net picking up on that the logistic regression model is not. And the question is, how can we improve our hybrid choice model so that it rivals the predictive power of the neural network while maintaining the same amount of kind of interpretability, or at least a similar amount of interpretability. And what this is really just the scientific method applied to the microcosm of a large data set, right? So in the scientific method, there's this kind of iterative procedure between kind of theory and experimentation, right? So you build a hypothesis, you get an experiment to test the hypothesis, you figure out where it goes wrong, and then you modify your hypothesis in order to, hopefully get fewer errors in the future. And what I want to talk about is this notion of residual analysis is very, very important, right? By saying that, okay, we got these things wrong, and we're going to look at how we got it wrong and say, okay, can we make the theory better? And we're just going to do that with the data set. And that's kind of, the standard methodology for exploratory data analysis today. So what I have here is the top residuals, the top errors between the choice model and the data. And I really want to highlight this top one. So here we have an empty car headed towards 4 pedestrians. And then on the other side is a dog and 3 cats. And the data says 99.4% of people would choose to go straight and kill the people, whereas our choice model says only 11% would. So clearly, the choice model and the data are very different here. And if our choice model is indeed wrong here, we need to kind of try to make it predict it correctly. But hopefully, like intuitively, this seems really weird that 99% of people would go straight. And if you look at similar dilemmas, it's not really like that. And this to us kind of suggests that it's noise. But unfortunately, we want to be kind of more systematic about saying that this is probably noise. And so if you recall, we also trained the neural network, and we can look at the neural network as almost trying to smooth out the data set and try to separate the signal from the noise. And the neural network actually just says, okay, only 16% of people will go and 16% of participants will go and kill the pedestrians in front of them. And this is actually really close to the choice model prediction and really close, really far away from the data. And this kind of suggests that, this data was actually noisy, because we think that the neural network is actually providing a better approximation of the data than the data itself, because it's just been trained on so many examples and it's been given the constraints that it needs to find some smooth function. We think that the neural network is going to be more accurate here. And if the neural network is more accurate here, then we should look at the errors between the choice model and the neural network, not necessarily the choice model and the data. Similarly, look at this second dilemma. There's an empty car headed towards an old woman and a pregnant woman that are crossing illegally, and on the other side is a dog and cat crossing legally. Now the data says 5% of participants will choose to kill the pedestrians. The neural network, the choice model says 59%, and the neural network says 25%. So whether the data or the neural network is right, the choice model got it wrong. We know that. But whether the correct answer is 5% or 25% is going to modulate the priority of this residual. Like, is this a really, really bad error that the choice model is making, or is this kind of an intermediate error? And again, we think that the neural network is kind of more accurate here. We've kind of looked at all similar types of dilemmas, and this 25% was really kind of smack dab in the middle of all these similar dilemmas. And so this kind of suggests a new methodology, which we're going to call scientific regret minimization. And the idea here is that, we collect, we run an experiment and collect our data set. We train our kind of psychological model in it, but at the same time, train some like black box machine learning model with a neural network, a gradient boosting tree, whatever is it going to achieve the highest predictive accuracy. And then rather than see where the simple model gets the data wrong, you're going to see the differences between the simple model and the machine learning model. Because the idea is the machine learning model is going to give you a better representation or a better estimate of the data than the data, or a better estimate of the true kind of underlying function than the data itself. And so the big idea here is we want to critique with respect to the model, now with respect to the data. And the intuition is that you really only want to penalize for mispredicting examples that are predictable, right? So if no model can predict something in the data, that's going to suggest that it's probably noise, and we shouldn't really penalize our kind of simple models for it. But if the neural network can get something right and the choice model gets it wrong, that means there's something in those inputs that the neural network is picking up on that it can correctly predict the output. And we want to try and reverse engineer what that feature is and try to incorporate that into our simple model. And so here, now I've said now I'm displaying the top errors between the choice model and the neural network. And something immediate kind of popped out to us is that here there's an empty car headed towards an illegally crossing person, and on the other side is a legally crossing animal. And the data and the neural network says that people primarily choose to swerve and kill the animal, but the choice model was predicting incorrectly. And we were kind of interested in why, but thankfully the choice model is only 22 parameters. We could kind of go in and see what was going on. And what we found is that the average penalty for swerving and the average penalty for illegally crossing across the whole data set is really, really large. And that actually outweighs the utility difference between, say, a man and a cat. And so as a result, the choice model is predicting that people would prioritize the legally crossing cat over the illegally crossing man right in front of the car. Clearly, this is not true. And so we need to kind of make our model better. And kind of our insight is, this is a humans versus animals problem. And a humans versus animals problem, it doesn't really matter if the animal is crossing legally and the human's crossing illegally, or you have to swerve to kill swerve to save the human. You're going to prioritize saving the human just in these humans versus animals problem. And so what we did is we looked at all of these humans versus these dilemmas, and if it was just humans on one side versus animals on the other, we gave it just like a binary flag. And we just said that, hey, we're going to add this feature to the model, and let's just give a boost to the humans when it's just humans versus animals. And there were 6 different of these axes that we kind of incorporated that the moral machine experiment manipulated. So there's like humans versus animals, there's male versus female, there's old versus less, young versus old. And so we incorporated these 6 axes into our logistic regression choice model, and that's plotted in the purple dotted line. And we see that we recover 50% of the gap between the original hybrid choice model and the neural network. So just by adding 6 parameters, and so now we have 28 parameters, we have achieved something, a model that's not too far away from the neural network, the black box neural network with kind of 2,000 parameters. And just as a check to see were these features doing something, we added these 6 features to the neural network as well. And what we found is that the neural network with the 6 features did better than the neural network without the 6 features at smaller data set sizes. But once the data set got big enough, those neural networks are virtually indistinguishable, and this kind of suggests that the neural network was kind of able to construct those features on its own. And so this is kind of an iterative procedure, and so we kind of did this loop kind of multiple times, and so now here is the second iteration. On the left are the largest differences between the data and the choice model. On the right are the largest differences between the choice model and the neural network. You can see that these dilemmas are very different, and we believe that the dilemmas on the left are mostly reflecting noise, and the ones on the right are actually the correct dilemmas to critique, and the correct dilemmas to critique and improve our choice model. And so we did this kind of again and again and again, and we were able to build a logistic regression model that had a similar accuracy in AUC to that of a neural network. But because we kind of, it was a logistic regression model, we knew kind of what all the features were, and we were kind of able to kind of identify some, interesting kind of moral principles and get some kind of explanatory insights into what people are doing. So what I just talked about was a method of kind of model building in this, with a large data set. And this is called, exploratory data analysis. But exploratory data analysis is really just one half of the scientific method, right? We also want to, after we construct our hypotheses, we want to, run experiments and test them and try to get at these like interesting manipulations. And so what I want to suggest to you is this method of residual analysis. I keep on looking at where our model and the neural network kind of diverged, and we were kind of able to identify some interesting new phenomena. And I'm going to talk about 3 of them today, called the dehumanization of criminals, the age of responsibility, and asymmetric notions of responsibility. And so we found these results in the data set, and then we kind of just validated them through independent pre-registered experiments. So I talked kind of, there was this like humans versus animal boost to the humans. And so, as I showed you, like that kind of increased the predictive power of our model. But then we started to err on a subclass of dilemmas, specifically when it was a criminal versus like an animal. And it seemed like participants were actually not giving that humans versus animals boost to situations like this when, say, a criminal versus a dog. And so to actually create a more, a better descriptive model of human moral cognition, we had to remove the humans versus animals label from like a criminal versus a dog, and thus kind of dehumanizing criminals in the eyes of our model. And to kind of experimentally test this, we kind of say that, criminal versus dog, what was the probability of saving the criminal, and then compared it to different humans versus a dog. So a homeless person versus a dog, an old man versus a dog, and a man versus a dog. And we did kind of all different crossing signal conditions and the different sizes of the car. And just systematically, we see that participants save criminals at a much lower rate than kind of other characters, suggesting that yes, criminals are going to be dehumanized and not given the same kind of moral worth that other kind of characters are. The second effect I want to talk about is called age of responsibility. So I want you to consider this dilemma here, where there's an old woman and a girl, and then another dilemma where there's an old woman and a girl and a woman. So most rational choice models are built off of a linear utility function, and here in a linear utility function would consider or rational choice models would consider these dilemmas to be equivalent, because in the right scenario, the women on the left and right sides would cancel out and would just reduce to the left scenario. And so we were interested, okay, if rational choice models consider this to be equivalent, do people actually consider this to be equivalent? And so what we did is we separated out into 3 different crossing signal conditions. So on the top are the old woman and the girl, and the bottom is the old woman, the girl, and the woman. And the left is the old side is illegally crossing, the middle is there's no crossing signal, and the right is the old side is legally crossing. And what we see here is people treat them the same when the old side is crossing illegally, or there's no crossing signal, but differently when the old side is crossing legally, or conversely, the young side is crossing illegally. And what we saw here is that when it's just a girl crossing illegally, people are not going to penalize her as much as if it's a girl and a woman crossing illegally. And this kind of brings back ideas about, if you're crossing illegally, you might be waiving your rights to protection. But say if you're just a child, like you probably just are not necessarily equipped with the knowledge that you are kind of waiving your right for moral protection, and people kind of want to compensate for that and subsequently kind of save them at a higher rate. And we kind of, so the data for this is a little noisy, but we kind of wanted to see this graph on the top right. We see this null effect between the no crossing signal and the legal crossing signal, and a significant difference when the young side is crossing illegally. And we did it for male and female, as well as for the car on the old side and the car on the young side. Lastly, I want to talk about this experiment called asymmetric notions of responsibility. So consider the case where the car is headed towards a woman and on the other side is a man. So this is going to be a male versus female problem. And similarly, let's look at the three different crossing signal configurations. So the woman's crossing legally, there's no crossing signal, and the woman's crossing illegally. And what I'm plotting, or what I'm reporting here, are going to be the percentages that the participants saved the man or chose to kill the woman. So when the man is crossing illegally, only 22.5% are going to save him. But when the man is crossing legally, 76.3% are going to save him. So now the question is, what percent saves him when there's no crossing signal? And what we see is it's going to be almost smack dab in the middle with 49.7%, almost in the middle of 22% and 76%. Now the interesting thing is going to happen is what happens when we switch the side of the car. So now the car is going to be headed towards the man, and on the other side is the woman. And again, so now there's going to be a little penalty for saving the man because the car is headed towards him. So when he's illegally crossing, there's an 11.3% chance of saving him. When he's legally crossing, there's a 67% chance of saving him. And now the question is, what's the probability of saving him when there's no crossing signal? So hopefully the way that I set it up, you're going to guess the mean again. And so that would be around 39%. And what we see actually with the data is dramatically less. That in this ambiguous condition, when there's no crossing signal, people save the man at a significantly lower rate, at 20%, actually very close to the rate that they save him at when he's illegally crossing. And the idea here is that when the car is going to be headed towards the higher valued individual, and there's no crossing signal condition, they're kind of given the benefit of the doubt. They're like, oh, there's a 50% probability that you're crossing legally. There's a 50% chance you're crossing illegally. But when the car is going to be headed towards a lower valued individual, in this case, they're going to be kind of almost presumed to have a higher chance of crossing illegally than legally, and then participants kind of act accordingly. And this kind of suggests some type of motivated reasoning. And so we kind of did this. We did man versus woman, old man versus old woman, large man versus male athlete, and large woman versus female athlete. And we got kind of all these, we wanted to see kind of a null difference in these green lines between the dotted line and this green dot, and the significant difference in the purple, showing that the illegal and the no crossing signal conditions are really treated the same for these lower valued individuals. So to conclude, basically what I've offered is a method called scientific regret minimization. And what I want to argue is that critiquing with respect to the data can be very sensitive to noise. And when we have a lot of data, there's bound to be, some noise in the data set, and we can use the neural network or whatever machine learning model to kind of smooth out the data and try to identify what the true kind of functional form is. But because this is not what we want our end product to be, we want our end product to be an interpretable psychological theory, we can then critique, say, psychological models with respect to this machine learning model and try and build a better model, and simultaneously identify kind of interesting new phenomena that we can then empirically validate and replicate. And lastly, just as a final note, I want to talk about, I think what really drew me to cognitive science was kind of, it was the interdisciplinary connections between kind of these 6 different fields. And I think something that I've kind of come to realize the more I work in psychology is that these fields are not as integrated as one as I would like. And I think a lot of this has to deal with kind of different values. So for example, psychology really cares about explanatory power, whereas artificial intelligence and machine learning really just cares about the predictive power of these models. And I think if we really want to build an integrative cognitive science, we need to kind of jointly maximize the values in these different fields. And so what I hope that big data can offer is to try to jointly maximize the explanatory power as well as the predictive power of our models, and thus kind of making the connection between psychology and computer science, and computer science and really all the other disciplines kind of much more integrated. And I think that will just lead to a better science and a more integrated science, hopefully. And with that, I'd like to conclude. Thank you all so much. So this was work done with my PI, Tom Griffiths, and second author, Josh Peterson. Thank you for funding. Thank you all so much for listening. And if you're interested, this paper was published a few months ago in PNAS, and I'm happy to chat kind of online right now. And I don't know if there's time for questions or not. I'll kind of leave that to Josh, but thank you all so much.
Thank you, Mayank. We have time for, I think, probably one question.
Cool. Naomi.
Okay, I'll bite. So I think this is really interesting work, and I think it's a nice idea to sort of use models as a constraint for sort of what sorts of variables you could be capturing. I'm wondering if you've thought at all about sort of how to deal with the fact that we haven't tried every model. So this is something that Thomas Schatz in my lab and I have been talking a lot about with some of our colleagues in terms of being able to deal with uncertainty in the sets of things that you've tried and how they relate to the actual world.
Yeah, so so the idea is that so there's two different layers. So we could be talking about the machine learning model here or kind of the psychological model. So the machine learning model, we just kind of hope that if we just have as few kind of theoretical commitments as possible, we can identify what's going to be the upper bound of the explainable variance. Of course, there's no kind of guarantees, but that's kind of what we hope, just fingers crossed, by training a neural network. I think a really interesting point that you make is and I think kind of a weakness of this current project is, maybe we kind of assumed a specific functional form for the psychological model. We assumed that it was going to be a rational choice model, like essentially a logistic regression model. And there's, that functional form might actually be incorrect. And the correct functional form might be kind of something else. And that's, I think, something that we're kind of interested in pursuing in the future is how can we actually try to identify the best kind of functional form as well. And I think I don't kind of really have a good answer for that besides kind of trial and error, but I think that's a really kind of important limitation of our work and something that we really need to address going forward.
Okay, thank you, Mayank.